All right, guys. So let's talk about Earth's magnetic field. Now, we know that we have geographic North Pole and geographic South Pole, and there's also magnetic North Pole and magnetic South Pole, and they're opposites, like we discussed in the previous chapter. So, for example, here we have South geomagnetic pole and South geographic pole. Well, geomagnetic pole is different from the magnetic pole. Geomagnetic pole basically described in terms of Earth magnetic field's influence in nearby space. So one of the things we have here is you can see, right, the North geomagnetic pole is near the Earth's north geographic pole, and South geomagnetic pole is near Earth's south geographic pole. Now, those magnetic fields uh, basically make the life pretty much on the planet possible. They play important role in making the planet habitable. Right. So because not only let's say they allow us to find the text, the direction using compass. Um, they also very important in terms of um, preventing the very high energetic particles from sun reaching the Earth's surface. So we talked about that in the previous chapter, how the magnetic field prevent all those energetic particles that come from the sun, basically reaching the part of the Earth where there's a lot of life. So those particles that reach Earth, they are charged particles. And we learned that charged particles can be pushed or pulled because of the magnetic field. So whenever they reach let's say this geomagnetic pole, or so this Earth's geomagnetic, let's say, sort of like, let's say, umbrella, right? So what happens here is those positive charged particles then are pushed in the direction of magnetic field, negatively charged particles pushed in the opposite direction of magnetic field, and they pretty much redirected toward the poles where there is very little life. And we learned last time that the effect of that, those aurora borealis, right? So basically the northern and southern lights. That's when those charged particles finally reach the Earth's atmosphere and they interact with the oxygen and nitrogen in our atmosphere. Now the question is that um, what exactly the reason? What is the reason that we have those magnetic fields? Well, there's a lot of research still going on, and we technically still not 100% sure exactly um, what is the main reason for that. But there are several sources that we can think of. So one of them is there's iron. There's a large deposits of iron ore, deep beneath surface. Okay, but there's also convection current in Earth's outer core. That means we think that there's a combination of those. So you can see, right? So the source of Earth's magnetic field cannot be large masses of permanently magnetized material. So that means it could be a combination of the iron ore deposits, the convection currents. Then we have charged ions, which is charged ions and ions and electrons circulating in liquid outer core. They would provide a magnetic field just like the current does, right? In a let's say in the loop. So for example, then here's a like a simulated image, right? That you can see how the magnetic field, right, that magnetosphere basically protects. So you can see more or less those are sort of like, let's say, those harmful particles. So when they come in, they kind of redirect it away from Earth or toward the northern and southern poles. Okay, that means there are different reasons for magnetic field, and this magnetic field that Earth generates, for example, in terms of the poles, North Pole, South Pole, even that is not, let's say, constant. The direction of the North Pole and South Pole, North magnetic and, let's say, I'm talking about magnetic poles, right? They also flip. So whatever we have right now for, if I come back, go back to the previous slide. Okay. Say this is the South magnetic pole. This is North magnetic pole. Well, 800,000 years ago, as early 800,000 years ago, those were opposites. This was north, this was south. That means this flipping of the poles happens quite often. You know, basically every million years or so, it pretty much changes. It flips, goes back and forth. And again, last time around 800,000 ago, 800,000 years ago, it happened, and it can happen again very soon. the magnetic field weakens sometimes, stronger sometimes, and scientists think there's a possibility that, quite soon, maybe not, like let's say during our lifetime, but maybe in a generation or two, the magnetic field, those poles can again flip into, south and north, basically changing their positions. All right. Another very important evidence of strong magnetic field is the rotation of a planet. So, for example, the the rate of rotation for Earth is higher than the rate of rotation for Moon. So then the Earth's rotation being faster gives you much stronger magnetic field. Remember, rotation is the spin on its axis. Earth spin on its axis um, with a period of 1 day. Moon spins on its axis with a period of 27, 28 days. Technically, Moon's rotation and revolution are exactly the same. It takes it about 28 days to go around Earth, and it also takes 28 days for it to rotate. So revolution is when object goes around some external body. That means Moon's rotation or Moon's revolution around Earth, or Moon's motion around Earth is known as a revolution. But Moon's rotating on its axis, for the Moon, for some reason, you know, it happens to be exactly the same. Well, the reason could be because of the tidal effects of Earth and the Moon. Eventually, let's say it's being kind of like locked because of that. Billions of years, the Moon being, let's say, revolving around Earth. But at this point, interesting fact is that when when Earth, sorry, when Moon is rotating and revolving, it does so at exactly same rate. So that's why as the Moon is going around Earth, exactly at the same rate it's rotating. So every time we look at the Moon, we always see the same face. That's because as it's going around Earth, it's also rotating at the same rate. So for us from Earth, we always see exactly same face of the Moon. If the Moon would rotate faster or slower, we would see, basically all around the Moon, but we don't, because it's always rotates such that when it's revolving, its rotation show us exactly same face. Also, because its rotation rate is slower, its magnetic field is weaker. For example, here I have Jupiter has much higher rotational rate than Earth. It has much stronger magnetic field. And you can see, right, Venus rotates more slowly than Earth. Its magnetic field is weaker. Again, one of the reasons that, let's say, some kind of celestial body has a strong magnetic field is because of its rotation. Because of the rotation, right, the rotation basically, steers those charges, and those charges as they're moving, they generate magnetic field. If there is no rotation, those charges not moving as fast. And remember, the flow of charges is what we define as current. So the flow of charges, the current, directly proportional to the strength of the magnetic field. That means magnetic field is stronger when those charges inside in the inner core or outer core are moving faster. All right. Another thing we can talk about here is kind of going back, from Earth. We have two conducting wires. If you have two conducting wires, then those conducting wires, if they have some small finite distance between them, they will experience a magnetic force because of the presence of another, a conductor. So for example, let me kind of draw it here so you guys can see kind of like from the beginning. So let's say you have a conductor 1, okay? And let's say this conductor has a current I1. Now, because this wire is has a current to the right, using the right hand rule, right? Using the right hand rule. So here's your thumb. You can see, right, your fingers then will curl, out of the page. That means what we have here is the current being to the right, you will have then your fingers curl out of the page. That means above the wire, the magnetic field it generates, that means this wire generates, will be out of the page. But then if you continue curling your fingers, you can see, right, then the below the wire, well, your fingers go into the page. That means magnetic field that it will generate below the wire, right, will be into the page. That means everywhere above it, the magnetic field is out of the page. Everywhere below it will be then into the page. That means this, let's call this B1, which is the magnetic field generated by the wire 1. Now, we learned that magnetic field at the point where this wire is, let's say, for example, some point right here, will be 0. That means it does not generate any magnetic field where the wire itself is, and it's never affected by that. But for example, if I bring another wire, so let's say here's wire, let's call this wire 2, and let's say it also has a current, let's call this current 2, also to the right. With the same right hand rule, I can see that if I curl my fingers, that means my thumb again in the direction of the I2, then my fingers will curl above I2 as coming out of the page. That means, for example, I'll think like this. Before doing this, let's talk about this. So when I bring that wire 2 and let's say place it at where the already I have magnetic field due to wire 1, then what I have is that I have a conducting wire with the current running through that's sitting in the region where there's external magnetic field. Now, if there is an external magnetic field, then I can use the other, second right-hand rule to determine that there will be a force acting on this wire. Okay. Now, that second right-hand rule will be like this, right? Remember, so you have your fingers in the direction of the magnetic, in the direction of the current. Then you need to curl your fingers in the direction of the outward magnetic field. Then your thumb will point in the direction of the field. I'm sorry, of the force. That means there's going to be a magnetic force. Sorry about terrible drawing, but there's going to be a magnetic force acting on wire 2 that will be downward toward wire 1. So that's why when you have this conductor 1 and 2, there's going to be a force acting on each wire, a force, magnetic force that will be toward the other wire if those currents are exactly in the same direction. Now, I showed you that how right now magnetic field generated by wire 1 exerts a magnetic force on wire 2 that is toward wire 1. Now let me show you how then, because there is a current running through the wire 2, it generates its own magnetic field, and it's going to be out of the page above wire 2, but into the page everywhere, below wire 2. That means that's a magnetic field generated by wire 2. And now you can say that wire 1 sitting in the region where there is a magnetic field generated by wire 2. And using the same right-hand rule, my fingers in the direction of the current 1, then I need to curl in the direction of wire 2, magnetic field 2, which is now into the page. Then my fingers will curl like that. All right, so then if I do that, my thumb will point upward. Again, you can see, right? Your fingers in the direction of the, current 1, which is to the right. Then you have to curl your fingers into the page. Your thumb basically will point upward. That means there's going to be force, magnetic force toward current 2 acting on wire 1. That means there's going to be an attractive force between those two. If the wires have opposite direction current, the force will be in opposite direction. That means it's going to be repulsive, which you can again figure out for using the right-hand rule. But one thing we can say here is this. So let's say again, kind of considering the, let's say the setup that we have two conducting wires. We're talking about two straight parallel wires. They're going to be separated by some distance a. That means like a small finite distance a. So then what we have here is there's a force acting on them. Remember, force due to a wire is the current times length times magnetic field. Okay, that means you can see, right? For example, force 1 is equals to current 1 times length times magnetic field 2. Okay, that means the force 1 is on the wire 1. So this will be force 1. So you can see, right? The force on wire 1 depends on the current running through the wire 1, the length of wire 1, but the magnetic field generated by wire 2. Because wire 1 will never have a force acting on it due to its own magnetic field. Force that it will have will be due to the external second, a source of magnetic field, which is B2. Same way, F of 2 will be I2L times B1. Okay, so I2L times B1. Now, one thing we have here is this magnetic force is action reaction force. That means it's exactly same magnitude, opposite direction for both of them. So we kind of can combine them, and we can assume that what we have is that you can say, right, F1 equals I1 L cross B, which is the magnetic force due to a straight current carrying wire, on the straight current carrying wire due to the external magnetic field. Then I can write it in terms of, since L and B are perpendicular to one another, I can just write it as ILB sine of theta, but sine of theta is 1 because they're perpendicular. Then if I write down magnetic field 2, remember we derived this, that magnetic field due to a straight wire is mu naught I divided by 2 pi times the distance. Well, that means if we're considering this magnetic field 2, then for magnetic field 2, this will be B2 is equals to mu naught times I2 divided by 2 pi A. That's why if I replace that for the magnetic field 2, that expression, then the force becomes, force 1 becomes, you know, I already have current 1 over there. Now I have current 2. That means the product of the current 1 and 2. Then there is a length constant, and then 2 pi times the A, which is the distance between those two wires. Okay. That means that's how we can calculate the force acting on wire 1. But, you know, it's going to be exactly the same if we calculate for force on wire 2. That means you can say that this is same as force 2. Okay. A lot of times we divide both sides by L, and to represent this as force per length, kind of get rid of the L from the other side, because we don't know how long the wire is, and a lot of times we don't really care. So that's why we can say force per length, which is equals to mu naught times I1 I2 divided by 2 pi A. So relatively straightforward equation. Just, you know, two wires, just one equation, calculate force per length. Okay. So again, rewriting, you can see, right? So we basically end up with this equation. All right, so this equation applies to both wires, and then when the currents are in opposite directions, the magnetic field, magnetic forces are reversed, and then the wires repel each other. That means two magnetic forces, two let's say wires in the same direction current, I1, I2, will be attracted to one another. But if you have two wires, I1 to the right, I2 to the left, these two wires then will repel each other. So the force will be repulsive force. So two current in the same direction, attractive, two current in opposite direction, repulsive. All right. Now, the magnetic force between parallel current carrying wires is used to define the ampere. So we talked about ampere as a unit for the current. Now, this is the official definition of the ampere, which is pretty much taken from this setup. So we have, imagine you have two wires that have a current running through them, I1, I2. So if you have basically two long parallel wires that have 1 meter apart distance, so they're separated by 1 meter, and we measure the force between them, which is, you know, probably the easiest thing, you know, to measure the force, right? There's force meters that we can use that. If we measure the force, and then there's a force acting on them, force per length, which is equals to 2 times 10 to the, sorry guys, this should be -7. So it's 2 times 10 to the -7 newtons over meters. So 2 times 10 to the -7 newtons per meters. Then the current in those wires will be exactly equal to 1 amps. Okay. That means if the force per length between these two wires, if the force per length is 2 times 10 to the -7 newtons per meters, then you can say that each current, I1 and I2, will have 1 amp. That's how we define ampere. Okay. And then from that, that's how we define coulomb. So the coulomb will be in SI units, right? For the charge, it will be if a conductor carries a steady current of 1 amp, the quantity of charge that flows through a cross section of the conductor in 1 second is 1 coulomb. Remember, current is equals to dq dt. That means dq is equals to I times dt. So if this dt is 1 second and you have 1 amp current, then 1 amp current, amount of charge going through that, some cross-sectional area A in 1 second, can be then defined to be exactly equals to 1 coulomb. All right. Now, here what we're going to do, we're going to talk about Ampere's law. So Ampere's law is analogous to the Gauss's law. Remember, when we started this class, we talked about Coulomb's law, and then we looked at some continuous distribution of charges, trying to solve some problems involving finding the electric field using the Coulomb's law. Remember how difficult it was. And then we learned about Gauss's law, which allows us to find same electric field for some of the same configurations, but in a much, much, much simpler way, using basically the concept of flux and the charges inside, right? So that's the Gauss's law. That means for highly symmetric configurations, finding the electric field was just a matter of like 2-3 lines of calculations. Where if I use the Coulomb's law to solve those, I needed to take the electric field as a vector component, basically do the all the substitutions and components and everything. You can go back and look at how tedious and difficult it was calculating electric field before we learn about Gauss's law and we learned how to apply that. Same idea here. That means we learned in the first part of this chapter how difficult it is to use Biot-Savart law to calculate the magnetic field due to several configurations. Well, one thing I have here is Ampere's law allows us to calculate magnetic field for similar configurations, but where the symmetry can allow us to make some simple assumptions, such as the magnetic field is constant and uniform around some kind of imaginary loop. So that's kind of what we have. You can write a simple experiment demonstrates that the current carrying conductor produces a magnetic field. Well, we know that. So now, remember, one thing we have here is, by the way, Ampere was actually the scientist who realized that magnetic field goes around in a circle whenever you have a current carrying conductor. So now we know, we take it as given that magnetic field goes, basically loops around a straight current carrying wire. But Ampere was actually the one that showed mathematically that that's basically what happens. It kind of curls around the wire, and then experimentally it was discovered. Obviously, one of the easiest way to discover that and to see that, which I always show that in my classrooms, is you take a compass and then you basically rotate around a straight wire, and then you can see that the needle of the compass basically tells you in which direction the current is moving. Because if there is no current in the wire, compass will only be just aligned with with respect to Earth's magnetic field. You turn on the let's say your power supply, close your like let's say switch, then you have a current running through the wire, then right away the compass basically detects the magnetic field generated by the wire. If it's very close to the wire, then the magnetic field is dominated by the magnetic field generated by the wire. Earth's magnetic field is relatively weak, so if you're very close to the wire, the compass pretty much will give you the direction of the magnetic field generated by the wire. Okay, so it technically gives you the superposition of the magnetic field, but because the Earth's magnetic field is weak and you're very close to this, the let's say the wire, you can then pretty much with the confidence say that what you're detecting here is the direction of the magnetic field generated by the wire. Okay, so that's kind of what we have. That means you can see, right, if you have a wire with no current, then look at all the you have 1 2 3 1 2 3 each side. You have 6 compasses. They all line up with the Earth's magnetic field. That means assuming right now the Earth's magnetic field is in this direction, so then that's why they line up in that direction. As soon as you have a current running through the wire, look, the magnetic field, that the green line, the green circle, right, around the wire, we don't see that. It's not something we can see, right? Just like electric field, we can't really see that, but compass can detect that. Okay, which is a little bit simpler compared to the electric field, right? There's no such device to detect electric field. We don't have, let's say, electric compass. So, but there's a magnetic compass, which is allowing you to detect the direction of the magnetic field, which is really good. So here's the picture C allows you to actually see if you let's say You have a conducting wire and you have a current running through that, and you have a bunch of iron filings in that region. You can see how those filings line up, right? There's kind of like circling around that wire. Now, what we have here is if you have a current upward in a, let's say, y direction, then you can see, right, the current, sorry, the magnetic field is counterclockwise, which again, what we can do here is we can see that from the right hand rule, right? This is your thumb in the direction of the current, then your fingers will curl in the direction of the magnetic field, which is, basically curling counterclockwise. Okay. So if we switch the direction of the current, then you have basically opposite direction magnetic field, which will be clockwise. Okay. Now, basically, remember, recall that Gauss's law can be used to determine the electric field in highly symmetric situation. Now, we're now going to consider the analogous relationship. That means Ampere's law does to the magnetic field what the Gauss's law did for the electric field. So we're going to find a relationship that some kind of imaginary, let's say, a loop that can be related to the magnetic field due to some kind of highly symmetric current distribution. Okay. Now, probably the calculations for the Ampere's law can be even simpler because this is not even, surface integral. It's going to be a line integral. Remember, the Gauss's law was the electric flux, which was integral of E dot dA is equals to Q enclosed over epsilon naught. Remember this equation, right? And this is technically was a surface integral, but which is, you can also write it in terms of two-dimensional, right? So like two, double integrals. So like E dot, technically it's dx dy, depending on, so, a little bit more advanced, let's say, classes, you can write in terms of like that. But for us, the Ampere's law, you can see, right, is going to be even a little bit simpler because it's a surface integral. So what we're going to do, we're going to consider the product, not a vector product, but a scalar product, B dot ds. Remember, this B dot ds is a dot product between two vectors, which is ds is a length element of some kind of, a path, right? And that path can be a circular path, can be a rectangular path, but some kind of, imaginary loop. Okay. So then what we do, we then do a dot product of magnetic field, which is tangent to that loop, and some kind of length element of that loop. Okay, so for example, you choose some kind of a loop like that, then you can say, all right, so here, this position, magnetic field is always going to be tangent. And then you can choose some kind of a length element like that, and this will be then ds. Then what we're doing here is we're then doing the dot product between those two vectors. Okay. Remember, dot product is always gives you a scalar quantity. So that means B dot ds can also be kind of written as B ds cosine of theta. Sometimes can be simplified to that. But the idea here is this. So for a small length element on the circular path, right, centered on a wire, which means that if I have a wire like this, let's say this is my, straight current carrying wire, I can think of it like this. So I can imagine that there's some kind of a circle, some kind of, imaginary loop around this wire. So then what I can do here is I can try to find then the magnetic field along this loop. Okay. That means along this path, the two vectors, which is ds and magnetic field, are always parallel. As you can see, right? If I take this position, here's magnetic field, tangent. And if I look at then ds, well, here's ds, parallel. They're all going to be parallel to one another. Then then we can write it as like this, B ds. Why? Because then cosine theta is also 1, theta is 0 between them. So we can always write this B ds. Now, then what I have here is that by symmetry, the magnetic field is constant in a magnetite on the circle. So for example, then if I have a closed integral of B dot ds, which can then simplify into just BDS, so it becomes BDS. And if the magnetic field B is constant and uniform, I can remove from integral becomes b times closed integral of ds. Now, remember, this is a closed integral of ds, which means that I'm integrating along this entire path, but it's a circle. That means I'm going basically around the length of that circle. So this integral is nothing but the circumference, just 2 pi r. And that's what we get. So this is my integral. Now, magnetic field, we know that due to a straight current carrying wire is equals to mu naught I over 2 pi r being the radius of that circle. Then those two, when you multiply together, 2 pi r cancel out. That means this integral of b dot ds is equals to that mu naught times the current. And the current here is the current that is enclosed inside that imaginary loop. Okay. Now that is known as Ampere's law. Ampere's law basically gives you, in terms of closed integral of b dot ds, and it relates that this integral to the current. So mu naught is just nothing but the proportionality constant. So it relates to the current distribution inside that imaginary loop. Okay. Now the idea here is that if you have a straight wire, right? For example, right? If you have a straight wire, you you want to relate the let's say your imaginary loop to the to the current distribution inside, but this equation will only be simple enough if the let's say configuration that you choose, let's say in this case that circle, that assumes that magnetic field is constant and uniform around along the path. Obviously we know that it is for if it's a straight wire and my imaginary loop is a circle. If I choose my imaginary loop something like that, that will be not the case, right? Magnetic field here is different than magnetic field over there because there's different distances. So this R1 is different from this R2. That means magnetic field here is different than here, than there. That means this integral cannot be simplified. I cannot remove that out of the integral. Okay, it's not simple enough because magnetic field is not uniform or constant along that path. So that's why don't use this. Use a type of configuration that allows you to have a magnetic field which is constant and uniform. All right, so that's why Ampere's law is valid for only for a steady current, assuming that this is not a time-varying current. Then even though Ampere's law is true for all current configurations, it is only useful for calculating the magnetic fields of configuration with high degrees of symmetry. Okay. Also, I should point out that, for example, this current here can be thought of as net current, because you might have two wires. Maybe you have two wires, or maybe you have three wires, right? And let's say if all of them in the same direction, you simply add them together. If one of them in opposite direction, then you subtract. Anything that's up or out of the page is positive. Anything that down or into the page is negative. All right, so let's look at then in terms of the conditions for the Ampere's law. Now, it's a path integration, right? It's a line integration. So we call this Amperian loop. Again, it's just like Gaussian surface. It's an imaginary, loop. So you just imagine that, let's say, for example, here's a straight wire and you say, okay, I want to find magnetic field at this point P. Now, what you can do here is that say, okay, so let's assume that there is, some kind of imaginary loop that has a radius of R. Well, that radius of R is exactly, reaches the position P. Then if I find the magnetic field on this, for this Amperian loop, it also gives a magnetic field of this point P, which is exactly what I want. That means what we can do here is I can apply Biot-Savart law to find the magnetic field at that point P, which we did. You can go back and look at part 1 of this lecture. But what I'm going to show you here is that it's much simpler, right, to use the Ampere's law to solve any of those type of things, if the configuration is highly symmetric. Now, again, you can see, right, for the integral to be a simple path integration, and that means magnetic field comes out of the integral and you're just doing the path integration, the sum of the conditions have to be satisfied. So must satisfy one or more of the following. The value of the magnetic field can be argued by symmetry to be constant over the portion of the path. That's a condition 1. That means you want the magnetic field to be constant and uniform so you can remove it. The dot product can be expressed as a simple algebraic product BDS, B times ds, because the field and length elements are parallel. Okay. The dot product is zero because the field and length elements are perpendicular. That means if you considering a magnetic field and length element, they're perpendicular. BDS, remember it's BDS cosine of theta, right? Technically, theta is 90 degrees for perpendicular vectors, so the dot product is zero. Then the magnetic field, condition 4, right? Magnetic field can be argued to be zero at all points on the portion of the path. Okay, that means exactly if the dot product is zero, one of the things you can say here is the reason it's zero is because the magnetic field is basically zero, at all points on the portion of the path. All right, so let's look at then a few examples and learn how we can apply the Ampere's law, to solve some of this. Again, it's very similar to the uh, examples that we looked at in terms of we are applying basically examples involving finding the magnetic field. Okay, different configurations. So here we have a long, straight, thin-walled cylindrical shell of radius r, carries a current I that is parallel to the central axis of the shell. Find the magnetic field, including direction, both inside and outside the shell. All right. So again, it's a straight, thin-walled cylindrical shell. That means what I have here is, let's say this is my cylinder. So it's not a solid cylinder. So it's basically a shell like this. Okay. Now, then the current I is parallel to the central axis of the shell. That means the current is thing like this. So I'm kind of, do it in terms of cost. So you can say, so the current is basically only in this region. It means, basically only in that, let's say inside the shell. That means inside is pretty much empty. But again, so it's sort of like a thin walled. So you can think of like there's only just one radius. So radius r. Okay. So that means the current here is basically like that. So we can apply Ampere's law, where I can choose two different Amperian loops. One will be such that it will allow me to find the magnetic field inside the shell. So let's say my loop will be something like that with radius, let's call that R1. And R1 is a radius of that Amperian loop that is less than the radius of the shell. And another one will be Amperian loop such that, well, let's call this R2, and this R2 will be greater than the radius. All right, so then I can then use my Ampere's law, where integral of B dot ds is equals to mu naught I enclosed. Okay. That means using the symmetry, we can try to find right configuration where we can assume that for this type of configuration, this particular uh, path integration will give me constant magnetic field. Now, this equation also assumes that on the right side is equals to mu naught times I enclosed. Okay, so by symmetry, we can see that the field is the same everywhere on this circle. For the radius less than this radius 1, R1 less than the radius of the shell, I can see that within my Amperian loop, there is no current. The current is only, remember, is inside that shell. Okay, that means pretty much on the surface of the shell. Inside, there is no current. So then I can say this is equals to mu naught times 0, which means integral of B dot ds equals to 0. Since technically delta ds, right? This ds cannot be zero because I do have a loop. This means that this is zero only because magnetic field is zero. That means magnetic field for this radius r1 less than radius is zero. That means there is no magnetic field inside the shell. Now let's look at for outside. Okay, that means I have Ampere loop big enough to enclose the entire shell. So for this one, R2, which is greater than the radius, then I can say that integral of b dot ds, closed integral of b dot ds, is equals to mu naught I enclosed. Okay, so from here, what I can say here is along that path that I have for the Amperian loop, magnetic field is constant. So looking at the left side of the equation, closed integral of b dot ds becomes bds, because also what I have here is magnetic field, and the ds element is going to be perpendicular, parallel to one another. That means, for example, if I choose magnetic field like this, then the path also, the ds will also be parallel to that. So this will be ds, and this will be the magnetic field. So then that product becomes just BDS. Magnetic field, due to symmetry, can be assumed to be the same everywhere on this circle. So it becomes B into closed integral of ds. And this is just basically the path integral. That means I'm integrating over the entire path. So it becomes B times 2 pi r2. So then this is equal to then mu naught times I enclosed, which means my magnetic field is equals to mu naught I enclosed divided by 2 pi r2. That means what I have here is that mu naught, my I enclosed is just basically total current I, then divided by 2 pi r2. And r2 is just basically any distance as long as it's greater than the radius. Then I can use that to find the magnetic field outside of the shell. All right. Let's look at now another example where we're not dealing with the shell, but we're dealing with a solid wire. So we have a long straight wire of radius r carries a steady current I that is uniformly distributed throughout the cross section of the wire. So we want to calculate the magnetic field at the distance r from the center of the wire. Usually I like to call this one, let's say R1, which is the one that is basically represents the magnetic field inside your conductor. And then we're going to talk about R2, which is the one that kind of represent outside of your conductor. Okay, so we want to calculate the magnetic field for those two different distances from the, with relative to the center, right? Relative to the center of the conductor. Now, what we have here is this. Again, because of the symmetry, the best shape I can choose is then a circle. Obviously, as I said, right? So any shape technically can be chosen for the Amperian loop. But obviously, if I choose like let's say a square or rectangle, um, well, magnetic field here is not the same as over there, right? Different distances. So it doesn't really help me. But if I choose then, for example, a circle, then I can assume that magnetic field is constant and uniform everywhere around it, around that, around the circle. Now, one thing I have important thing to understand here is this. Let's start with the second condition, R2 greater than or equals to the radius. So if I choose this, it's just straightforward, basically closed integral of b dot ds. That means, you can see, right? This is basically for the path. Or let me see. I guess, I can switch this around because uh, the picture here says that loop one is outside and loop two is inside. That means this is one and this is two. So let's do that. Okay. So this is loop one. So b dot ds is equals to mu naught times I enclosed. Now, along that loop one, magnetic field is everywhere constant. That means magnetic field is always going to be tangent to the path like this, but whatever the magnetic field that I'm choosing is going to have the same strength because it has same distance r or R1, right, relative to the center of the wire, which means I can replace this, you know, the dot product with just integral of BDS, which can be written as magnetic field out of the integral, then closed integral of ds, and this is just a closed integral around, integration, the path integration around the loop becomes b times 2 pi r1, or just basically, again, any r greater than or equal to radius. This is equal to then mu naught times I enclosed, which then gives me b is equals to mu naught I enclosed over 2 pi r1. Now, I enclosed is all the current inside my Amperian loop, which then pretty much will include all the current that is in the conductor. So it's going to be mu naught I divided by 2 pi r. Okay, so let's say as long as r is greater than equals to the radius. Okay, that's the answer for the first one. Now let's look at then the second one, which is in terms of finding the radius or the magnetic field inside the conductor at some distance r2 from the center, but r2 something that is less than the radius. Okay, that means we are looking at basically this second Amperian loop. Okay, now for this one, then again what I have is that integral of b dot ds is equals to, well, this is equal to then mu naught times I enclosed. Now let's look at the left side of the equation first. Okay, so the left side of the equation is, again, we can assume that magnetic field is going to be constant everywhere on the circle. So it becomes BDS, and magnetic field and DS going to be parallel to one another. That means usually BDS, then B can come out, become just integral of DS, which one will be B times 2 pi R2, for example. That's the left side of the equation. Now let's look at the right side of the equation. It equals to mu naught times I enclosed. Now, question here is, what is I enclosed? Is I enclosed equals to the I? Well, no, not for R2 less than the radius. Because what I have here is the current that is enclosed in my loop will be this much current. And the current that is not part of the loop basically will be all that red. So all that red is the current that is outside of my Amperian loop. That means for this particular magnetic field, right, that I'm considering, only the current that blue region, right, counts in calculating the magnetic field. Then I need to find how much of the total current is inside that, blue region, or inside that my Amperian loop. Well, for that, what we do here is we remember that J, which is the current density, was defined as the current divided by the area. Now I have two areas. One, let me say that area one is then, let's say, the blue region. And area two is then the total region of the conductor. That means A1 represents only the region that I have for my Amperian loop. A2 is the total conductor region, okay, the surface area of the conductor. Current density then is equals to the total current divided by total area. So let's call this, I2. But then this will be also the current density, right? Current density will also be equal to the ratio of my current enclosed, right? My current enclosed divided by area one, because my current here is only in this area one. That's my area one. But their ratio is also equal to the current density. That means the ratios are equal to one another. That means I can say then current enclosed is equals to A1 over A2. That means area of my Amperian loop divided by the total area of the conductor, then times total current. Basically rearranging this for the I enclosed. Now what I have here is my Amperian loop's area is pi r square. The area of the total conductor is pi radius square, then times total current. Obviously pi's will cancel out. Then what I have here is this. So B times 2 pi r, or let me kind of write it like that. So then this will be equal to then mu naught times I enclosed, where I can rewrite I enclosed as r square over the radius square times total current. Okay. Then from here, I can see that the r square can be canceled out, sorry, from one side, not both sides. Okay. Um, let's see. So it will cancel there. So it will cancel here, but over there, just basically the square. So then what I will have here is this. So B will be equals to then mu naught times I divided by 2 pi radius square, then times r. Okay. So then this will be the magnetic field inside a solid conductor. So where r is basically less than the radius. Okay. So then the graph for this type of conductor, like let's say the magnetic field distribution, how the magnetic field behaves, will be like this. So going from 0, r equals 0 to r equals radius, that will be inside. And then beyond that will be outside. So then we can see that magnetic field is proportional to r inside. Because one thing we have is that assuming that this, the radius is constant, current is constant, the magnetic field then will change as a function of r. As r changes, magnetic field linearly increases. It will increase until r is equal to the radius, because B is proportional to r over there inside the conductor. Beyond that, if you basically then considering outside of the conductor, then you can see, right, B proportional to 1 over r. So B proportional to 1 over r, so it's going to be sort of like a drop like this. That means, again, inside and outside, completely different. If you have a shell, there was no current inside, so there was no magnetic field inside, which is kind of similar, when you talk about if you have a conductor. So for example, right now, if I look at electric field inside the conductor, a metal conductor, I should get 0. Okay. And if I look at the electric field inside the shell, I would also get 0. But there is a magnetic field inside the conductor because there is a current. So there's actually, a flow of charges, which gives you current, and you have a magnetic field. Let's look at another example, and this is a device called toroid, which is often used to create an almost uniform magnetic field in some enclosed area. So you can see, right, this device consists of conducting wire wrapped around a ring, a torus, made of non-conducting material. Okay. So you can see, right, the conducting wire wrapped around, and is basically creating a loop, creating, like, let's say, a lot of loops, and the magnetic field will be, remember, so let's say if you have a loop like this, the magnetic field kind of goes like, let me use a different color for the magnetic field. So if there's a current in the loop, then magnetic field will be like that, then like this, then like that, then like this. So that's how the magnetic field will be. But if you have a bunch of them, then in a way you're going to have a magnetic field that will kind of go like that inside this toroid device. Okay. And if you have large number of n, the magnetic field technically can be relatively uniform. Okay. Now, what we do here is this. We want to find the magnetic field, right? So we want to find the magnetic field, and we want to find magnetic field inside and outside. So let's say that we have a toroid that has an n number of turns. Okay, so we want to find the magnetic field in a region occupied by the torus, a distance r from the center. That means what we want to do here is find the magnetic field, let's say somewhere over here. So then in order to do that, we just use then Amperian loop. Okay. So that my Amperian loop, again, kind of goes like this. Okay. So then for the, again, n representing number of turns, then I can apply Ampere's law, close integral of B dot ds is equals to mu naught times I. But since what we have here is we have n number of turns, so technically you can say that this is n times I. So we can put it like this. So it is n times I, n representing basically the number of turns. Okay, so it can be, incorporated in this, Ampere's law equation. All right, so it's a circle where the magnetic field is constant and it's parallel to the ds element. That means this becomes basically b integral of ds, which becomes b 2 pi times r, and this equals to then mu naught n times I. That means magnetic field is equals to mu naught n I divided by 2 pi r. Then this will be the magnetic field for the toroid having n closely spaced turns of wire. So this will be the magnetic field some distance r from the center of the toroid. Okay, you have to understand, right? So for example, if I try to find magnetic field somewhere in this region, there's, I'm not going to be able to basically find anything. So that's why we try to find r such that it's basically inside the toroid, because magnetic field is constant and uniform inside that device. All right, another very useful and important device is the solenoid, which is a long wire wound in the form of a helix. Okay, so reasonable, it gives you a reasonably well, uniform magnetic field. Sort of like analogous to parallel plate capacitors. Remember, if you have parallel plate capacitors and you charge them such that one plate is positive, the other one is negative, then you get electric fields, right, inside, which is relatively uniform and constant. Solenoid is the same device for the magnetic fields. So we can get a uniform magnetic field produced inside the solenoid, okay, which will be then proportional to the current and number of turns inside. If I put, like, let's say 100 turns, then replace it with a 1000 turns, which is 10 times more turns, then I'll get 10 times stronger magnetic field. So we're going to see that strength of the magnetic field is proportional to the number of turns I have, which means that I can increase or decrease the strength of the magnetic field depending on, in terms of the type of device that I have, type of number of turns I have, and things like that. All right. Now, one thing we can do here is you can write each of the turns can be modeled as a circular loop. Okay, so let's say one loop, another. So this is basically sort of like what we can do. Think of it like a solenoid. So this is a solenoid as a device that has a radius r. So let's say a radius r like this, and it has a length L. Okay, and then the magnetic field will depend on which direction is the current. Is it clockwise or is it counterclockwise? So we're going to see that we can think of it like, let's say here's that solenoid device, right? So depending on which direction is the current, then we will have a magnetic field, which technically then can be modeled as even a bar magnet. So you can see, right, north and south for the bar magnet, and you can see, right, where the north, the magnetic field coming from the north goes into the south, coming from the north goes into the south, technically then goes through that as well, right? But the idea here is solenoid becomes similar to that. So the magnetic field will go through the solenoid such that it will come out. And remember, the region where the magnetic field comes out, going to be then north. The region where the magnetic field going in, then going to be south. That means you can even have sort of like the north and south poles for the solenoid. All right. That means we have a turns that are closely spaced, okay, and it has a finite length. That means length is basically sort of like, let's say, uh, sometimes can be compatible to the radius, sometimes can be much larger than the radius. So you have to kind of also pay attention into that as well. Now for here, think like this. So we can again model it as similar to the bar magnet. It can generate magnetic field. The important thing here is the magnetic field inside then can be constant and uniform, and it will depend on how many turns you have. What is the current? That means the strength of the magnetic field. And it also will depend on a number of things, like let's say the radius and the length, right? So it can depend on those things. So let's look at in terms of how we can find the strength of the magnetic field inside the solenoid. So what we do here is this. Imagine, let's say, if you come back over here, imagine you are taking a knife. I don't know how to represent that, but think like this. So you take a knife or something that you can use to cut exactly through the center. So take it from here and just cut it in half. Okay, so just basically cut it in half. So then this is basically what we have. So this here is the magnet, the solenoid exactly cut in half. Okay, so like a vertically down like that. So then if you do that, you can see, right, on one end you have the magnetic, the current coming out, and the other end current, it goes in. Because remember, we cut it such that we cut it in, basically exactly in half, and this is, what we had, right? So the loops were like this. So then current comes out, then goes in, comes out, then goes in. So that's kind of what we have. That's why one side is all the currents out, the other side all the current in. Okay, that means one of the solenoid behaves like the north pole, the other one south pole. That was basically here, north and south. And what we can do here is, as the length of the solenoid increases, the field becomes more and more uniform. So here's what we have. This is for the ideal solenoid. The turns are closely spaced. The length is much greater than the radius. Okay, that means if you do that, then you can kind of ignore the radius. Okay, so the field outside the solenoid is negligible. Only inside, that means if I look at the electromagnetic field over here, I can technically say it's zero if it's an ideal solenoid. Only the magnetic field inside counts. And the field inside is uniform. Okay, remember parallel plate, we only cared about electric field inside. Technically, there's electric field outside as well, but we never really cared about those because they were negligible compared to the field inside. Same idea here. So to find the magnetic field strength inside the solenoid, what we do here is we apply Ampere's law. Okay. So, but because of the type of configuration we have, for example, right, if I use a circle, then this will be a relatively poor, let's say, shape for this type of, configuration. Same thing, for example, if I basically use something like this. So I have loop 2, loop 1. So the idea is that we can apply Ampere's law to the circular path whose plane is perpendicular to the page. We can use this to show that there's a weak field outside the solenoid. Okay, which technically then we can more or less ignore because if it's very weak compared to the field inside, we can say it's negligible, can be ignored. Let's then look at loop 2. Loop 2 then can allow us to find magnetic field inside. With loop 2, we have a rectangle that can be used to represent 4 different segments of the rectangle. Here's segment 1, here's segment 2, segment 3, and segment 4. Each segment then can be analyzed independently. So think like this. We have a rectangular path with the length L and width W. That means we can say that this is length L and the width here is W. All right. What we'll do here is then we're going to apply the Ampere's law, that equation, integral B dot ds, for each of those segments. Okay. One thing I can have here is this. if I look at each segment independently, then I can find, let me use it, let's say for example, right? So segment one. See, for segment one, this will be my ds. For segment two, this will be my ds. For segment three, this will be my ds. And for segment four, this will be my ds. So ds1, ds2, ds3, and ds4. Remember, so when I apply this closed integral of b dot ds, I can see one thing. If I'm adding them all together, right? If I'm adding them all together, for the loop one, sorry, for the, not loop one, just the segment one of loop two, for the segment one, magnetic field is basically, you can see, right? Magnetic field here is, let's say it like it's By hat, right? Because it's pointing upward. Well, ds1 is equal to then, I'll put it here, ds1 is equal to then dsj hat. And this two then, that means for the segment one, they're parallel. So I can say it's closed integral of bds. Okay, so technically I can even, you know, replace this ds here is with dy. The idea here is that both of them in the same direction. For loop two, or sorry, segment two here, my d, my b is equals to, again, so j hat, but my ds is equals to then d, dxi hat. And the dot product of those two will give me 0. Well, same thing can be applied for segment 4. That's also now negative I hat, magnetic field is j hat, they're perpendicular, dot product is 0. That means left side of the Ampere's law, B dot ds, is 0 for segment 2 and segment 4. Non-zero for segment 1. Well, let's see for segment 3. Will that be also 0? Well, it will be 0, but not because the ds, but because there is no magnetic field in that region. So when we apply this equation, we can say that there is no magnetic field in that region, so that integral equals to 0. Right. That means what we end up with is this. If we apply all of those that we just did, right, we can see that in the region, so basically the contribution along the side 3 is 0, which is this one over here. Contribution from side 2 and 4 are also 0 because the ds perpendicular. That means the only surviving side here is side 1. And closed integral of b dot ds equals only for the side 1, b dot ds. But we just said, right, magnetic field is constant and uniform in this region. That means along the entire path, magnetic field is constant. That means I can remove that, becomes integral of ds. This is just a path integration, so it becomes just bl. Okay, that means the right side of the Ampere's law involves the total current. So that means this is the left side, bl, and the right side is just a total current that passes through each surface, right, or bounded by the path integration. That means the left side of the equation, we got bl. The right side of the equation, mu naught times n times I. That means what we end up with, divide both sides by L, then we have a magnetic field which is equals to mu naught Ni divided by L. Okay. That means magnetic field is proportional to the number of turns, current, inversely proportional to the length. But one thing we do here is we represent N, which is a number of turns per length. So this becomes N over L, some kind of quantity N over L. So then we replace our equation with this N, lowercase n, which is the number of turns per length, rather than capital N, which is number of turns, and divide by length. Okay. That means usually what we do here, we say magnetic field inside a solenoid equals to mu naught N times A. Again, remembering that lowercase n is number of turns per length. Okay. So this is then the magnetic field of a solenoid. All right, so one thing we have also, I kind of mentioned, the Gauss's law that we use for the um, finding the electric field. We also have a Gauss law in magnetism. Okay, so let's see what we have. So let's say some kind of arbitrary let's say surface, and let's say there's a magnetic field through that some kind of area, small area of interest. We can define that to be dA. So you can see the vector is parallel, perpendicular to the surface of that area of interest, and the magnetic field has some angle theta with that. So that means what I can calculate here is in terms of magnetic field and dA. So now what I have here is I have B dot dA, which is the dot product between magnetic field and the dA, which then can technically be as B dA cosine theta. Okay. Remember, this is then defined, can be defined as magnetic flux. So this can be defined as magnetic flux. Just like electric flux was defined as E dot dA, which was EA cosine theta. Okay. Now, what we have here is, right now, if I just consider this particular, area where there's a dA and there's a magnetic field, there is a flux. Okay. But if I calculate the total flux through the surface, the total magnetic flux, then I can write it in terms of total flux equals integral of B dot dA. Now, what I have here is there is a big difference now between electric flux due to the electric field and magnetic flux due to the magnetic field for a closed region. If I'm considering, so this is kind of like how we can write, if I'm considering closed region, then magnetic flux, you will see, is total magnetic flux. It's going to be different compared to the electric, flux. But before that, let's look at this in terms of this integral for this magnetic flux, which is an integral of B dot dA. Remember, the idea is that where flux equals BA cosine of theta, just like the electric flux, depends on the number of field lines going through some area. So for example, here, the theta between magnetic field and dA is 90 degrees. So then flux will be 0. Here, the theta is 0 degrees. Then flux will be basically just B times A. So you get a maximum flux. So the units for the magnetic flux is defined as a Weber, which 1 Weber is equals to 1 Tesla times square meters, because it's magnetic field times area, so Tesla times meter square. All right, so let's look at an example here. We have a rectangular loop with of width A and length B. And this rectangular loop is near a long wire carrying a current I. The distance between the wire and the closest side of the loop is given as distance C. So then the wire is parallel to the long side of the loop. And we want to find the total magnetic flux through the loop due to the current in the wire. Now, what we're going to do here is we're going to find the magnetic field, the magnetic flux, and we cannot just use magnetic flux equals BA, okay? Because one thing we have here is the magnetic field is not uniform inside this loop. And that's what we want to find, right? Magnetic flux through this loop due to the current in the wire. So all this green, the vectors are the magnetic field generated by the wire that is to the right of the wire. Remember, if you have your thumb in the direction of the current, then you can see, right, your fingers will curl like this. That will be in the direction of the magnetic field, which will be into the page everywhere to the right of the current. Okay. But one thing we know is that the magnetic field, if you remember, right, is mu naught I over 2 pi r, which is due to the straight wire. Means that this magnetic field is stronger than that magnetic field. That means magnetic field is not uniform inside the loop. So that means what we need to do is we need to integrate in order to get the total flux. Okay, because technically what we have here is magnetic flux. Remember, is integral of P dot dA. Okay, and what we need to do here is we need to basically integrate this in order to get the total magnetic flux. What we do here is we choose a sort of like a patch. It has a size dr. That means let's say the thickness is dr, and its length here is b. Okay. So, and it has a distance r from the wire. That means what we have here is we have our loop, then we just choose some kind of a patch like that is distance r and has a thickness dr relative to the wire. So then let's kind of talk about in terms of how to set up our equation. So the flux, magnetic flux, equals to, right, so basically integral of P dot dA, magnetic field due to well, one thing we know that is that you can see, right, current, and if I'm choosing sort of like, let's say dl for my patch and magnetic field, they're perpendicular. So dA and dA and magnetic field are parallel to one another because magnetic field is perpendicular to the surface itself. So this is BdA. Remember, the dA vector will be also into the page, so then they will be parallel to one another. So magnetic flux can just basically in terms of BdA. But magnetic field is mu naught I over 2 pi r, and this is then dA. So one thing I have here is that if I'm looking at then in terms of dA, okay, remember dA is not the area of the loop. This is pretty much A, not dA. So A is the entire area of the loop. dA is then the area of the small patch. Okay, so that's why I wrote this as, the thickness dr and the length b. So then dA is just basically b dr, right? Length times width, and its thickness is just basically dr. That means dA is b dr. That means what I can do here is I can rewrite this in terms of then mu naught I over 2 pi r, then b dr. Okay, which means then my magnetic flux is equals to integral of mu naught I b over 2 pi then dr over r. This means you can see sort of like, let's say what I end up here is I end up basically some constant then dr over r. That means all that can come out, and then integral going to be then in terms of dr over r. So then I can set up my limits. That means I'm going to be integrating from distance c all the way to distance c plus a. That means from this end to the other end. This will be like c, then c plus a. Well, mu naught I b over 2 pi. And if I do the integral, this is just 1 over r, integral of 1 over r. So that's going to be then ln of r with respect to c, then c plus a, which then will give me mu naught I b over 2 pi, then ln of a plus c divided by c. Okay, which then can also be simplified in terms of mu naught I b over 2 pi, ln of 1 plus A over C, which is pretty much the same thing. All right, so then this will be the total magnetic flux for that loop. All right, so continuing with Gauss's law in magnetism, one of the things we have here is that if you're considering a magnetic field due to some kind of source, which is either bar magnet or a straight wire or a current loop, remember we always talked about how the magnetic field is continuous, which is different from electric field. Electric field is not continuous because electric field has a starting point and it has a termination point. Remember, if we have a positive charge and a negative charge, electric field starts from positive, goes and ends at negative. So starts positive, goes and ends at negative, and so on and so forth. That means there is a starting point and there is an end point, so like a termination point. So if I choose some kind of Gaussian surface, then what I can see here is then over here I have a flux. If I do closed integral of E dot dA, because what I have here is I have electric field going in, but nothing coming out. So I'm going to have a negative flux, but still I'm going to have a non-zero flux. Now, if I do the same thing for a bar magnet, so let's say I take one of the poles, north or south, then I look at closed integral of B dot dA. Well, it means that I'm looking at total contribution of the magnetic fields for this surface. Well, what I have here is I can see that whatever comes in from one end, like let's say, right, whatever comes in on one end, will exits on the other end, which means if I break it down into surface where the magnetic field enters and the surface where magnetic field exits, I'm going to get positive flux when it enters, negative flux when it exits, but they're going to be exactly same, and I'm going to get zero. Okay. That means what we have is that the net magnetic flux through a closed surface surrounding one of the poles or any other closed surface is zero. So that's why what we have here is the net magnetic flux through any closed surface for the Gauss's law in magnetism always gives you B dot the integral of B dot dA equals zero for a closed path, right? That's kind of like key for the closed surface. So that means this integral, closed integral of B dot dA, will always be equals to zero. All right, so next we look at some of the concept that kind of requires modern physics, let's say quantum physics. So we're just going to be briefly looking at some of this, later concepts. So here's what we have is a classical model of atom. So imagine over there is the nucleus, and we have an electron orbiting the nucleus. Kind of goes around the nucleus. Well, one thing we know here is because there's some kind of sensation of the rotation, that particle, since it has velocity like this and r vector like that relative to the center of rotation, remember the angular momentum was equals to r cross p, which is basically the distance or the vector r relative to the center of or pivot point of the center of rotation cross the momentum, which is basically also then r cross this quantity mv. Remember, the p is the linear momentum, which can be represented in terms of mv. So this can technically be simplified into r mv, which is distance times mass times speed of the particle, to calculate the magnitude of the angular momentum. And the direction of angular momentum was always perpendicular to r and v, just like torque, just like magnetic force. Angular momentum was also always found using a right-hand rule as well. That's why if you have your fingers in the direction of r, curl in the direction of the velocity, then you will see that angular momentum points upward. Okay. Now, another thing we have here is this. Because this is an electron, one thing we can say here is that if it's a moving electron, it generates magnetic field. Okay. And there's a current, current of orbiting electron. And that current will be in opposite direction because of electron being a negative charge. Then the current here is basically in opposite direction. Now, what we have is that orbit has area A. That means, this is the area A of the orbit. And then what we can do here is we can calculate electron's angular momentum about the nucleus, where we take the mass of the electron and then the orbital speed, right? So basically looking at in terms of that. But also we can calculate the moment, the magnetic moment of this electron, which is equals to then mu, and that's equals to current times the area. That's basically being the magnitude of the magnetic moment. And because this charge is a negative charge, the magnetic moment will be in the opposite direction of the angular momentum. Okay, so these are the equations for the angular momentum and the magnetic moment of the atom. Now, one of the things we have here is, as I say, right, so these are, can be described using the quantum mechanics, so quantum physics. So what we have here is that you can see, right, the fundamental outcome of the quantum mechanics tells us that there's orbital angular momentum of this particle, right, is quantized. And it's equals to a multiples of h bar. H bar is sort of like a modified Planck constant. The Planck's constant, this is this h. Then if you divide h by 2 pi, then we get this modified, Planck's constant, which is h bar. Now, in terms of then what we have here is this is the smallest non-zero value of electron's magnetic moment. So can be represented with this equation. So the mu is equal to square root of 2 times E, which is the charge of the particle, its electron, right? Divided by 2 times its mass, then time Planck's constant. Okay. That means what we have here is, if I take this calculation, then I can get smallest non-zero value of electron's magnetic moment. Okay. So this result tells you that there is a basically magnetic effect due to some moving electron. That means a single electron moving around. Remember, so technically this is a classical model of atom, right? So electron not really moving around, but for example, it does have angular momentum. So let's say if it's moving around, then there is a magnetic field that generates, there's a magnetism. Then the question is that every single object in the universe is composed of electrons. Then why aren't we magnetized? Well, that's because there are magnetic field or magnetic moment, right, due to not just one but a lot of other different type of electrons, some of them moving in the opposite direction, and the magnetic moment of one then can be canceled by the magnetic moment of the other one. And generally most of the that's the case for most of the let's say objects that are not magnetized. That means the magnetic moment of one electron is canceled by the magnetic moment of another electron. One of the things we have also for the, let's say the electrons or protons or basic subatomic particles, is that they also have what we call spin. Okay, so the spin is another intrinsic property of those subatomic particles, and they also contribute to the magnetic moment. So that means what we have, you can say that classically the electron might be viewed as spinning about its axis, but again, that's some of that classical, interpretation of how the subatomic particles behave. It's not entirely accurate, but it's good enough that we can use them to describe some of the things. Okay, so then what we have here is You can say, right, the magnitude of angular momentum is associated with the spin, and the magnitude of angular momentum is due to its orbital motion. That means that they're not only going around the nucleus, they're also spinning. Okay, so that means you have kind of like, let's say, two things that's going on. And I also already mentioned, right, in terms of, let's say, this, rotation versus revolution, right? So you have spin, which is the rotation. There's a revolution, so that means angular momentum when it goes around the nucleus, and then you have the spin that when it's spinning around, and both contribute to the magnetic moment. Okay, then this is the equation. So this is the magnitude of the spin angular momentum of an electron, which is then, that means you have a spin angular momentum, and you have the rotational angular momentum, so due to the orbital motion. So orbital angular momentum, and then the spin basically angular momentum. And what we have here is the value of the magnetic moment is given for the spin as charge times h bar divided by 2 times mass of the electron. And atomic magnetic moment can be expressed as multiples of Bohr magneton. So EH over 2 mass of the electron, so becomes 2.97 times 10 to the negative 24 joules per Tesla, okay, which is equivalent to amps times meter square. That means we can basically combine, right? So we can combine magnetic moment that we calculated due to its orbital motion and due to its spin. And the idea here is they contribute into the magnetism of the system. But then most of the objects, right, because of the type of configuration they have, that let's say they have even number of electrons, wherever goes in one direction, there's another one which goes in the opposite direction, and they cancel each other. There are some, let's say, system where you can have maybe, like, let's say, odd number of electrons. That means that we have one extra or something like that, and that can technically contribute a little bit to the magnetism. All right, so here are the magnetic moment of some atoms and ions. So you can see that, for example, hydrogen has a magnetic moment, helium 0, neon 0, and so on and so forth. So these are some of the in terms of the atom or ion. Okay. And that's again the value of the Bohr's magneton. Okay. Now we can talk about in terms of how some objects technically are magnetized, others are not. So what we have here is that you can see, right, we have ferromagnetism, which is a small number of crystalline substances exhibit strong magnetic effects. So like iron, cobalt, nickel, and those are, different other, let's say object like that, they have strong magnetic, let's say effect. That means that's why, for example, you can have a magnet pick up, pieces of iron, right? So the paper clips and things like that. Now, what they do, they contain permanent atomic magnetic moments. Okay, so we can see that in terms of a diagram here, where we can think of, like, let's say, some domains. For example, here's what we have for an unmagnetized object substance. So the atomic magnetic dipoles are randomly oriented. So think like this. Those are, each one here is a different domains, like that, where the arrows basically represent the magnetic moment of each one of them. Okay. Now, when you have then some kind of external magnetic field, then external magnetic field, for example, here can make some of those, orbits, as not orbits, like domains, right? Basically be affected by the presence of this external magnetic field. Okay. Then they can align, some of them can align themselves with the magnetic field. And they can align, then they get, their domain is become enlarged. Those ones that are not aligned, their domains, become smaller, even they shrink. So you can see, right, for example, here's a domain that's kind of aligned, here's a domain that's kind of aligned, then they become bigger. This one is not aligned, becomes smaller. That means as external field becomes very strong, you can basically increase the domains in which the magnetic moment is not aligned with the field becomes very small. And then you can see, right? So if this is, again, let's say if we increase the magnetic field strength, then the domains that are aligned basically dominate the region. Okay. That means the sample may retain the net magnetization in the direction of the original field, even after we remove this external magnetic field. That means that system then becomes magnetized. Okay. So one of the things we have here is you can see, right, that there's what we call Curie temperatures for several ferromagnetic substances. And in terms of then, the reason we have in terms of temperature dependence, because remember, so technically we're talking about, the motion of the atoms, the spin. And one of the things we have here is that, that so like ordinary temperatures, the thermal agitation is not sufficient to disrupt the orientation of those magnetic moments. But then when temperature, increases and reaches some kind of critical temperature that we name as a Curie temperature. So then after this, beyond, or you can think of like, let's say when it reaches this critical temperature, the substances start losing their magnetization. Okay. And so below this Curie temperature, the magnetic moments are aligned and the substances become, ferromagnetic. But above the Curie temperature, the thermal agitation basically starts affecting those domains. And it becomes, if it's great enough, then it can cause random orientation of the moments, and then the substance can become paramagnetic. Okay, paramagnetic means that they have just a weaker magnetization. So this is sort of like, let's say, paramagnetic, and you can see that, what we have here is there's just a weak magnetism resulting from presence of the atoms or ions with permanent magnetic moments. That means what we have is that those magnetic moments permanent, but they're not entirely aligned. So there's a weaker magnetic, let's say, weaker magnetism effect from those. Okay. All right. So we have basically paramagnetism. Okay. So in terms of beyond this, you can also have diamagnetism. This is when the external magnetic field applied to a diamagnetic substance. So they have the weak magnetic moment induced in a direction opposite applied field. So this causing diamagnetic substances to be weakly repelled by a magnet. Okay. Now, this diamagnetism, you can see, right, present in all matter and effects much smaller than those of paramagnetism or ferromagnetism. Okay. So again, these are sort of like, let's say, different type of substances that can affect, sort of like a magnetic effect. And you can see, right, so basically we have ferromagnetism, paramagnetism, and diamagnetism. And you're talking about, let's say, in terms of, hopefully you can see that why there is a magnetic effect. And, let's say in terms of a substance becomes magnetized because of the domains, right, align themselves. And that's pretty much how we also know how the Earth has changed its, let's say, south and north poles, because we can find, let's say, substances, right, let's say that have a magnet, let's say they have their domain magnetized due to Earth's magnetic field, and they have not been extracted. Let's say they're maybe deep, beneath the surface. And when we extract them, we can see that their orientation is different from the orientation that we have presently. That means they have been magnetized by the previous magnetic fields, and let's say the direction of the magnetic field that we have for Earth. And they basically still, keep that particular orientation. And that's how we can pretty much verify, and we can date them, and we can see when it occurred. And let's say the oldest that we have that still represents the, let's say, different polarity was about 800,000 or 900,000 year old, let's say, ferromagnetic, let's say, substances. And then that's how we can pretty much scientifically, right, verify those type of phenomena. And obviously, we can date other rocks. We can go back as millions of years and hundreds of millions of years, and we can look at them, which we can compare them, and we can see that technically Earth has changed its poles, right? Hundreds of times over this period. But that's basically beyond the scope of this class.